In June 2026, NASA's James Webb Space Telescope trained its instruments on a planet 217 light-years away and immediately proved every previous model wrong. We thought we understood how hot this planet gets. Webb showed us we were off by hundreds of degrees. This is HD 80606b, the most eccentric planet ever found, and for the first time, we watched it burn in real time. HD 80606b was discovered in April 2001 by Michel Mayor and Didier Queloz, the same team that found the first exoplanet. But even among the thousands of worlds catalogued since, this one stood out immediately. 4 times the mass of Jupiter, roughly the same radius. And an orbit so extreme, astronomers didn't know whether to call it a planet or a comet. Here's what that orbit actually looks like. Over 111 days, HD 80606b swings from 0.88 astronomical units, roughly Earth's distance from the Sun, all the way into 0.03 AU. That is 10 times closer than Mercury. If you stood in the upper atmosphere of this gas giant at its farthest point, the parent star would look unremarkable, a bright point against the black. Similar to our own Sun seen from Earth, but then the plunge begins. Over the following weeks, that unremarkable star grows and grows. By the time HD 80606b reaches periastron, its closest approach, the star fills 30 times more sky than our Sun does from Earth. 30 times. The entire dayside hemisphere faces a single unbroken wall of stellar fire. The numbers behind this orbit are staggering. The planet's eccentricity is 0.93. For context, a perfect circle is 0. Earth's orbit sits at 0.017. Halley's Comet, the most famous elongated orbit in our solar system, measures 0.967. HD 80606b is a world 4 times Jupiter's mass, moving on a trajectory more extreme than most comets. And that trajectory creates something genuinely terrifying. During the periastron passage, the planet receives 1,000 times more stellar radiation than it does at a pastron, a 1,000-fold increase in insolation, most of it delivered in a window of roughly 6 hours. In 2009, NASA's Spitzer Space Telescope caught HD 80606b during a periastron passage, and what it recorded redefined what we thought planets could survive. The dayside temperature exploded from 800 Kelvin to 1,500 Kelvin. That's roughly 530 degrees Celsius to over 1,200 degrees Celsius in 6 hours. Let that sink in. This planet heats up by nearly 700 degrees Celsius in the time it takes to watch a long movie. The atmosphere does not warm gradually, it flash heats. And that sudden thermal shock does not just make the planet hot. It creates shockwave storms. Winds tear across the atmosphere at 11,000 miles per hour, 5 kilometers per second, over 14 times the speed of sound in Earth's atmosphere. Entire weather systems spawn, rage, and dissipate in hours. The substellar point, the spot directly facing the star, becomes a permanent hurricane of superheated hydrogen and helium, rippling outward in concentric shock fronts that wrap around the entire globe. Then, just as abruptly, it is over. The planet swings back out. The star shrinks in the sky. The temperature plummets toward 500 Kelvin. Over the next 55 days, HD 80606b drifts toward a pastron, where it receives roughly the same amount of sunlight Earth does. A brief 55-day winter before the next plunge. Spitzer's 2009 observations were groundbreaking, but they were also limited. Spitzer saw the planet as a single point of light. It could measure the overall temperature spike. It could not resolve what was happening inside the atmosphere, could not see the chemistry changing in real time, could not map heat distribution across the planet's surface. For that, we needed Webb. We are about to get into what Webb actually found, and this is where things get genuinely strange. If you want to understand how a planet survives being flash-fried every 111 days, subscribe now. We release a new space documentary every single week. In 2026, a team led by Tiffany Kataria at NASA's Jet Propulsion Laboratory pointed Webb's MIRI instrument, the mid-infrared instrument, at HD 80606b. Their plan was ambitious. Observe the planet before, during, and after periastron. Catch the entire roasting cycle in unprecedented detail. What they found shocked them. The temperature spike was even more extreme than Spitzer had suggested, an additional 1,100 degrees Fahrenheit beyond previous estimates. Kataria told the American Astronomical Society in June 2026, Webb has shown that the planet's increase in temperature was even more extreme than we anticipated based on Spitzer data. The models were wrong. Not slightly wrong, significantly wrong. This planet gets hotter, faster than anyone had calculated. But MIRI was not the only instrument watching. A separate team, led by James Sikora at Lowell Observatory, used Webb's NIR spec, the near-infrared spectrograph, to study the planet's atmospheric chemistry across its entire 111-day orbit. Their 2025 paper in the Astronomical Journal revealed seasonal atmospheric changes more dramatic than anything we see on Earth. As HD 80606b approaches its star, its atmospheric chemistry literally reorganizes itself. Molecules stable at a periastron dissociate under the flash heating. Cloud layers vanish. Carbon monoxide and water vapor shift their abundances as the temperature climbs. The planet's atmosphere is not a static envelope. It is a dynamic, responsive system that transforms cyclically every 111 days, like clockwork. And here is what makes this scientifically invaluable. Exoplanet atmospheres are notoriously difficult to study. Most planets orbit at relatively constant distances, with relatively constant temperatures. Watching their chemistry change takes years, if it is observable at all. HD 80606b compresses that entire process into 6 hours. Laura Mayorga of Johns Hopkins Applied Physics Lab put it directly. Observing a planet like HD 80606b is actually very efficient because its unusual orbit allows us to gather data under varying conditions in just hours and apply those findings to other hot Jupiters. This single planet is a natural laboratory, a stress test for atmospheric physics that would take decades to replicate on any other world. So how does a planet 4 times Jupiter's mass end up on a comet's orbit? The answer involves a cosmic accomplice. HD 80606, the parent star, is part of a binary system. Its companion, HD 80607, orbits at roughly 1,200 AU, 30 times farther than Pluto is from our Sun. The leading explanation is the Cosmo mechanism. Over millions of years, the gravitational influence of that distant companion star gradually pumped HD 80606b's orbital eccentricity higher and higher, tilting and stretching its orbit into the extreme oval we see today. The planet did not form this way, it was sculpted. Slowly, inexorably, by the quiet gravitational tug of a star so far away it barely registers as more than a bright dot from the planet's sky. This matters because HD 80606b is not alone. It belongs to a growing class of eccentric Jupiters, gas giants on highly elliptical orbits that challenge everything we thought we knew about how planetary systems form and evolve. Every one of these worlds tells us something about the violent, chaotic processes that shape planetary systems, including potentially our own. Here is the bottom line. HD 80606b is not just an astronomical oddity. It is a window into physics we cannot replicate in any laboratory on Earth. Every 111 days, this planet undergoes a thermal cycle that exposes the fundamental behavior of matter under conditions we can only approximate in computer models. Webb proved those models incomplete. The next step is refining them. Future periastron passages will be observed with even greater precision. Kataria's team is already planning follow-up observations with NARCAM and additional MIRI spectroscopy. Each pass adds a new layer of data, and everything we learn from HD 80606b applies directly to the thousands of hot Jupiters discovered across the galaxy. One planet, 111 days, a 1,000-degree temperature swing, and an orbit so violent it creates shockwave storms visible from 217 light-years away. That is HD 80606b, the planet Webb watched burn.